Last time we finished developing an RLS filter. There are a few things that we haven't discussed that are important to discuss. One of them is how do we pick lambda? Another is how do we initialize this filter? With the LMS adaptive filter we initialized our weights to 0, but now we also have other quantities. We have the, for example, the p n minus 1 or pn to initialize. And so we'll talk about those in this particular lecture. But before we do that, let's spend a moment and talk about what happens with the error. We have the two errors, the a priori that we labeled alpha, and what we will now call the a posteriori error. And that was E of n. Okay, so for the a priori error, this is essentially what the LMS algorithm computes. It's just our desired signal minus the weights that we've computed to date prior to our update times our input signal. Of course, it's our LMS algorithm doesn't really compute that because it's going to have different weights, but it's the same form of the equation. And then we have the error that we defined that we're trying to minimize, and that's based on our current weights after we've done the update times x of n. So these two errors obviously are related, and the question is which one is going to be lower? We will assume for now that lambda is equal to 1. And then we can note, and I know this isn't quite trivial, so it's not quite fair for me to do it, but I'm just going to, in interest of time, note that there's a factor that relates to these two errors, and that factor is nu is equal to 1 over 1 plus x transpose n p n minus 1 x of n. And we can also note that nu is going to be greater than 0, and it's going to be less than or equal to 1. So the magnitude of E, our posterior, is always going to be less than or equal to the magnitude of alpha. Now we did put a few details under the rug there. The first is, what about lambda? Do we always want lambda to be 1? Well, it turns out that we're going to want lambda to be close to 1, but it's rare that we would want it to be exactly 1. And the problem is, if it's less than 1, that would show up right here. And if it shows up right there, then we have some quantity that's less than 1 plus a positive quantity. We would have to guarantee that that positive quantity is large enough that the denominator is greater than 1. Otherwise, this isn't going to hold. For now, let me just say that we will typically choose lambda to be close to 1, and that x transpose P x transpose is going to be significantly larger than the difference between lambda and 1. In other words, lambda plus that quantity is always going to be greater than 1. And so, in general, this relationship holds. It's just a lot harder to prove, but hopefully that little discussion will be enough to convince you that going forward, this is a reasonable assumption to make. Well, that leads right into this discussion about how do we choose lambda. As you recall, we have Rx of n is equal to the sum from the time we turn on our filter till n of the outer product of our x's weighted by our lambda to give us that easy recursion. So we'll consider several things. Suppose lambda is equal to 1 and n gets large. Well, in that case, our x of n is also going to go to infinity, which means that p of n is going to go to 0. Let's go back and look at our weight update equation. What's going to happen there? It might be easier to see here. If p goes to 0, then g goes to 0. And if g goes to 0, the weight updates go to 0. The weights stop updating. Okay, maybe that's what we want. If we have a stationary system, that means that we've converged and we want to stay there. Now suppose that lambda is approximately equal to 1, but is less than 1. Okay, what happens there is Rx of n gets large, but it doesn't become infinite. And Pn would accordingly be, since it's the inverse of Rx, it's going to be small. In this case, the weights continue to update very slowly after time. They may be fast at first. There is something subtle about this particular situation that will come up later when we talk about the square root RLS algorithm. And that is, we're dealing with p. If p is very small, then round-off errors can become a problem. And we'll see later that when there are round-off errors in p, it can violate some of our assumptions, which are that p is a positive definite symmetric matrix. And once that assumption no longer holds, although I haven't seen that it's really obvious from these equations, but the whole thing kind of falls apart. Primarily in our G update right here, if P is symmetric positive definite, then we're going to have a positive number there and everything's fine. If round-off errors cause it to be non-symmetric positive definite, then it's possible that that's negative. If that's negative, then G grows inappropriately large and could even become negative or close to infinity or something crazy like that. And in those cases, the filter actually diverges. And it's not because there's anything wrong with the theory, it's because there's something wrong with the numerics. And we're going to deal with that later. Finally, suppose that we have a small lambda, that it's much less than 1. In that case, we will have Rx n is possibly ill-conditioned. To give you some intuition about that, Rx is made of the sum of outer products. In order for it to be full rank, there must be at least capital N, where capital N is the number of columns and rows of Rx. There must be at least capital N outer products summed together, and those need to be independent. And the eigenvalues are going to be a function of these outer products. If those outer products are multiplied by something that's very small, and some of them are multiplied by something that's very large, it's going to cause a large eigenvalue spread. So, if that's ill-conditioned, then we're going to have wild variations on the solution. In other words, it's going to bounce all around. So typically we want lambda then to be near 1, but not equal to 1. And the exact length that we want, or exact value, may differ, but I typically see lambdas on the order of 0.95 to 0.99 and in that area. And as you get closer to 1, it makes a difference. So the difference between 0.95 and 0.98 is akin to the difference between 0.98 and 0.99. Okay, so that's lambda. What do we do now for initializing p? One thing that you may note, looking back at this, is that although we had to have recursive updates for RDX and recursive updates for RX, those are all folded into the equations that we have now. And the only thing that shows up in here that we need to initialize would be our initial weight vector W, which we can still initialize as 0 if we like. We'll talk about other options. And our P. We're referring to P of n minus 1, but we need to figure out where that begins. So what do we do to initialize P? Ideally, we could just set P of n is equal to Rx inverse n at some point. And so we could calculate a certain number, move forward, maybe P samples, build up an estimate of Rx, find the inverse, and that would be our starting point. Since we're talking about starting at time 0, what would we do? Well, we could do something like this. We use m samples of x before starting the filter to form an initial estimate of Rx 0. Then we just compute the inverse. Then P0 is equal to Rx 0 inverse. One solution. Well, we've gone to all this work to avoid doing inverses, so that may or may not be what you want to do. An alternative is to just let P0 be an identity matrix or something like that. Let's see, I guess I'll continue this on the next page. So this works out as we can let P0, actually let's start this way. We start with Rx of 0 is equal to delta I. So in essence, we're initially assuming that our signal is white, and we'll choose a small delta. Okay, so then what happens as we update our Rx? So Rxn is now going to look just like it did before, except we're now summing from 1 to n minus I, xn, x transpose of n, plus delta lambda to the n. And so this delta lambda to the n is going to cause this term to disappear fairly rapidly as n grows. And if delta was small to begin with, then we're fine. So if we're going to do that, we're never going to explicitly do our Rx. Instead, this means that we want 1 over delta times I for our P matrix. So we want P to be large. Looking back at this system, if P is large, then G is going to be effectively close to 1. And as we've seen back here, P is actually going to then decrease at a fairly good rate to where we want it to be as the delta lambda n times I dies out.